Okay, so we're going to look at the relationships between the thermodynamic parameters that we have introduced so far in this lecture. So far what I've told you is that the change in the Gibbs free energy is equal to the change in internal energy plus pressure volume minus Ts, right? And so long as you keep the temperature and pressure constant, then the change in U plus PV minus Ts is literally equal to the first law of thermodynamics when you bring everything to the left side of the equation. So, in other words, the Gibbs free energy at constant pressure and temperature is going to equal du plus PdV minus TdS. And one thing to remember is that du plus PdV was literally the definition that we had for the enthalpy. In fact, because the pressure is constant, du plus PdV is the same thing as saying d of u plus PV, right? That was literally the definition we used to derive the enthalpy of the reaction. So in other words, the change in the Gibbs free energy is equal to the change in the enthalpy minus the temperature times the change in entropy. And this equation is actually one of the master equations of thermodynamics. It actually allows you to tell the spontaneity of a reaction, and it's based on the enthalpy as well as the entropy of a reaction. So going back to the examples that I was kind of hinting at before, if this equation is correct, then what we have here should work out in terms of the calculation. And so the enthalpy, that is 1299.5, we input that in kilojoules per mole. The entropy is negative 216.14, but that's in joules per mole Kelvin. So we need to divide that value by 1,000, meaning that the value you input into the equation is 0.21614 as opposed to the 216. Now this is assumed to be a room temperature, and I didn't say anything about temperature in regards to the reactions, but the little superscript dot that you see here, that implies that the temperature is 298. So multiplying the entropy in kilojoules per mole Kelvin by the temperature in Kelvin gives you the following values: negative 1299.5 kilojoules per mole for the enthalpy, and positive, right, because negative and negative turn positive, positive 64.41 kilojoules per mole for the TdS term. So since the first term is negative and the second one is positive, this is technically a subtraction. You end up getting a value of delta G of negative 1235.09, which is pretty much on point with what we got before by using the delta H's, delta S's, and delta G's of formations. So as you can see, either way, whether we use the master equation or if we have the delta H's, L's, and G's of formation values, we can get to the same value. So that's kind of cool to confirm that. All right, now I kind of taunted you with this idea of the entropy of the universe, and the fact that trying to find the entropy of the surroundings seems like a fool's errand, something impossible to achieve. But what I want to show you is the following. We have delta S of universe being equal to delta S system plus delta S surroundings, and at the same time we have delta G system being equal to negative temperature times delta S system plus delta H system. And once again, remember, the system stands for reaction. So this looks kind of similar in format. In fact, if you divide both sides by negative temperature, you end up with the following equation: negative delta G system over temperature is equal to the entropy of the system minus delta H system over temperature. And although this isn't necessarily the case for other situations, here it actually works out that the entropy of the universe is literally equal to the negative delta G system over temperature. And the delta S surroundings is also equal to negative delta H system over temperature. So by introducing the Gibbs free energy, we have actually completely getting around the problem of trying to calculate the entropy of the surroundings, and instead, by focusing entirely on the system and nothing but the system, we could literally find out the entropy of the surroundings and the entropy of the universe as a whole by applying the formulas that I'm providing right here. And of course, delta S surroundings is negative delta G system over T, delta S universe, excuse me. Delta S surroundings equals negative delta H system over T, and delta S system is still delta S system. So this is a very nifty way of getting to those particular entropy values. But the most important part of this all is that the master equation of thermodynamics, delta G equals delta H minus T delta S, is ultimately a rephrasing of the second law of thermodynamics. The second law of thermodynamics, which is delta S universe equals delta system plus delta surroundings, is the same thing as delta G equals delta H minus T delta S. You can see here, just by dividing everything by negative delta T, we have the same format. So the Gibbs free energy is nothing more than a corollary of the second law of thermodynamics, and as such, it tells us about spontaneity altogether. Alright, so I'm going to show you an example where we actually go after each variable. We have already found delta H of the reactions, delta S of the reaction, delta G of the reaction for the combustion of acetylene. Reaction stands for system, right? So just think of them as synonyms. And so what we're going to do is we're going to use that information to find out the different parameters, right? We have delta S universe, which is negative delta G system over T. So we take the delta G value, change it to joules, by the way, so multiply by 1,000. So you have technically 1,235,100 joules per mole, that's negative, all divided by 298 Kelvin. And the whole thing gets multiplied by -1. So we end up finding out that the delta S of the universe is positive 4145 joules per mole Kelvin. And this is actually key, because what we discussed at the very beginning of the lecture is that positive values of delta S universe imply that the reaction is spontaneous. So what this also means is that the delta G reaction, if that is negative, then the process is spontaneous, because after all, delta S universe is equal to the negative of delta G. Alright, so keep that in mind, delta G negative or delta S universe positive, spontaneous process. We could also find the deltas of the surroundings by dividing delta H of the system by temperature and multiplying by -1. And much like delta G, we change the kilojoules to joules, multiply by 1,000, divide by 298 Kelvin, and negative become positive. So this is delta S of the surroundings, which is also positive. So even though for the reaction, the entropy of the system was negative, which generally speaking, negative entropy does not good in terms of spontaneity, the delta S of the surroundings completely overrules the delta S of the system and allows the reaction to still remain spontaneous, in spite of the fact that the delta S of the system is negative. Alright, now let's talk about spontaneity. Because delta S of the universe has to increase for the process to be spontaneous, and the fact that delta S of the universe is equal to negative delta G system over T, this tells you that delta G has to be negative for the reaction to be spontaneous. Alright, so negative delta G or positive delta S universe, that's a spontaneous process. Positive delta G or negative delta S universe, that's a non-spontaneous process. So we're going to look at the particular situations where you could end up with a spontaneous process or a non-spontaneous process, and we're going to do it in a very qualitative manner. We focus on the master equation of thermodynamics, delta G equals delta H minus T delta S, and we see what happens when the reactions are exothermic. Now, if the reactions are exothermic, delta H has to be negative. But delta S is not restricted. Delta S could be positive or it could be negative. That's independent of the enthalpy. So we look at both cases. We see what happens when delta S is positive. We see what happens when delta S is negative. And because you're multiplying delta S by negative T, if delta S is positive, minus T delta S will have to be negative. And in combination with a negative delta H, you will end up with a delta G that will always be negative. And as a result, you have a reaction that will always be spontaneous, no matter what the value of the temperature is. On the other hand, if the entropy is negative, negative TdS is going to end up being positive. And now you have counteractions taking place. So since the enthalpy is what allows delta G to remain negative, you want to keep the temperature low so that you don't overrule what the enthalpy is doing. And so the process will be spontaneous if and only if you keep the temperature low in this process, but it could easily be positive if the temperature is just a bit too high. Now for exothermic reactions, there's a similar approach. Delta H has to be positive, and the entropy could be positive or negative. In the case where the enthalpy is positive and entropy is negative, negative entropy will give you a negative T delta S value that is positive, and because of that, the delta G value will always be positive, and in other words, it will never be spontaneous. But for the case where the signs are the same for enthalpy and entropy, whether they're positive or negative, that's when you can get into this situation of being potentially spontaneous or potentially non-spontaneous. All right, so the idea pretty much boils down, at least for the two events right here, right? So for these two events where you have ambiguity, for you to be spontaneous, you have to have values of delta G that are negative. For you to be non-spontaneous, you have to have values of delta G that are positive. And if you're going to be able to cross over between those 2 points, then you have to go through the neutral ground, which means that you have to go through delta G being equal to 0. And so this becomes your reference point of view for the ambiguous cases, the cases where delta H and delta S have the same sign. All right, and the idea is this. 0 is going to be the point where you switch over from spontaneous to non-spontaneous, or vice versa, from non-spontaneous to spontaneous. So you literally let delta G equal 0, and you solve for the temperature. When you do that, you're going to end up with delta H equals T delta S, which means that delta H divided by delta S is equal to the temperature. And what this means is that based on this temperature, you're going to be able to tell below this temperature, something's going to happen. Above this temperature, something's going to happen. And you will only do this type of calculation if and only if both delta H and delta S have the same sign. Whether they're both positive or negative is irrelevant, but they both have to have the same sign. All right, so going back to these things here. For the case where delta H is negative, which is good for delta G, you want to make the temperature as small as possible. So in essence, you want to make the temperature less than the reference value. And in the case where the enthalpy is positive, you want to make the temperature as high as possible, because it's through the entropy that you will make delta G negative. So here you want the temperature to be greater than the reference value. And so this is how the whole thing will play out, right? And once again, if delta H and delta S have the same sign, you divide delta H by delta S, make sure that the units cancel out, and then you apply this rule. Less than the reference value, more than the reference value, depending upon the value of delta H. Okay? So let's do a few examples and then we'll finish this video. So I'm showing right here the Hess's law reaction, right? We have delta S reaction, delta H reaction for the formation of C2H6O. And what we're going to do is we're going to apply delta G to it. And the idea right here is that entering the values, right, you have negative for both entropy and enthalpy. So that means that you're in that ambiguous realm. So what we need to do is calculate the value of the reference temperature. We divide delta H by delta S, and since the units are not the same to begin with, you just make sure to change one or the other. In this case, I changed delta H to joules per mole. That was just my choice. You could have easily changed the entropy to kilojoules and keep the delta H the way it was. That's totally up to you. But what's going to happen is that the negative values are going to cancel out. You're going to end up with positive temperature, as you should, because this is Kelvin temperature. And you find out that the reference value in this particular case is 804.1 Kelvin. Because the enthalpy is negative, that helps out delta G. So you want to keep the temperature low. In particular, the process will only be spontaneous if the temperature is below 804.1 Kelvin, which is the reference value. All right, let's do a few more. Here we have values for entropy and enthalpy for the next reaction. Once again, here we have a positive value for delta H and a negative value for delta S. Since they're not the same, either we're going to have an always spontaneous situation or an always non-spontaneous situation. In this case, negative entropy multiplied by negative temperature is positive, plus positive delta H gives you positive delta G, which means that this process will never be spontaneous. Next case, the values of delta H and delta S in this example are the same, so we need to find out the value of the temperature. Divide delta H by delta S. Make sure to change your delta H to joules per mole, or vice versa, change your delta S to kilojoules per mole, whichever you prefer. The negatives are going to cancel out. You're going to end up with a temperature of 3000. But this time around, okay, so delta H is negative, so you want to make sure to keep the temperature low as to not affect your delta H. So you want the temperature to be below 3006.5 Kelvin. All right, the next example, we have positive values for both. Because they're both positive, that means that we have that ambiguous situation once again. So you want to find out the reference temperature, divide delta H by delta S. Once again, I'm changing kilojoules to joules. You end up with a value of 1749.5 Kelvin for the reference temperature. Since the enthalpy is positive, that is messing up the spontaneity of delta G. So you want to actually increase the temperature as much as possible. Specifically, you want the temperature to be greater than 1749.5 Kelvin. And that will make the process spontaneous. Okay, and here's another example. The values of delta H and delta S are negative and positive respectively. Because they're different, you don't have to find the reference temperature. That only happens if both of the thermodynamic parameters have the same sign. But since the enthalpy is negative, that makes delta G negative. Since delta S is positive times negative T, that gives you an overall negative term. So delta G will be negative every single time. So this is guaranteed to be spontaneous every single time. All right, so with all those examples, we have covered almost the full extent of thermodynamics. We have one more lecture that dwells with it. But now you have the full extent of the laws. The first law, the second law, the third law, and technically if you want to be thorough, the 0th law of thermodynamics, which is basically heat flow from hot to cold stuff. Alright, so I'll see you in the next video.